And welcome back. This is Mr. Wakefield. We're in the second half of section 7.3 right now. We got 4 more problems to go here. Okay, all having to do with sums. Okay, I know that because 3 of the problems have sigma letters in them. And then number 6, it doesn't have a sigma letter, but you can see that we got a bunch of things being added together there. So all of these are dealing with adding together terms of a sequence. Let's talk about those sigma letters here first. And let me pull that out for you here. You see here that when your sum, and again, this is just for geometric sequences right here that they're talking about this. Okay, when you have a sigma letter and then the thing that you plug into to the right of the sigma letter looks like this right here, where the b is a constant and the r is as well, and then the variable is in the exponent only. Okay, see how the variable here is I. It indicates that at the bottom here. Remember, your variable is always down here below the sigma letter, as we've seen before. If the variable is only in the exponent, the exponent could be I minus 1 as well, okay? But if the variable is in the exponent and you have constants in these two spots, then that means that it's going to be a geometric sequence where R is the common ratio, okay? And that's why they call it R. Just to give you a quick example here, you don't have to write this one down right here, but just a quick example. Doesn't this look like what we just talked about here? Okay, doesn't see how you got B and then the bracket and then the I and you got 4, 2, and I. So it looks like that. Okay, why would that be a geometric sequence automatically? Well, let's take a look at the first 4 terms that you get when you plug in I equal to 1, I equal to 2, 3, and 4 as well. Okay, these are the terms that you would get here. I calculated them. Okay, notice though that if you look at these first 4 terms, that it's definitely geometric. And I know that because 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. So clearly, it's a geometric sequence with what? With R equal to 2. Okay, so my point is that not only is it a geometric sequence when it's in this form right here, but that R number there inside the bracket, that is your actual R number, okay, which is why they call it R. That is the common ratio. That's the thing you multiply by to get from one term to the next in the geometric sequence. So let's try that right now, okay? Let's flip our worksheet over. There it is right there, number 5. And you can see that this also is in that same form when you got a constant times another constant in a bracket and then the variable here. The variable this time is j, same as this j down here. So that's why you know that that's the variable. Again, the variable is always down here. So since this is the same letter, it's got to be the variable too. So how do you figure out what the sum is? Okay, again, you can use the same formula as we did up here. You just need to know a few things here, and we can figure those things out. Remember, we need to know what A1 is. We need to know what the N is, which we do. Okay, N is equal to 5 because it's clearly adding up the first 5 terms here from 1 to 5. And so, remember, the N tells you the last term here. Sum of the first 5 terms, that means the N is 5, and then it would go here. And then you just put the R in there, which we also know. What is the R in this case? Because of the fact that it's in this form right here, that means that, as we just mentioned a minute ago, the R must be equal to 2/3. But what is the first term? We're going to need to know that as well in order to plug it into the formula. Is it equal to 243? Not necessarily, okay? It's not always going to be that way. It depends on how it's set up. The best way to find out is just to plug in j equal to 1, okay? Since the sequence is supposed to start out at 1 here. Remember, it always starts with this number down here. So the first term's got to be the one that matches up with this number down here. If I plug that in, let's write that down. If I plug that in, I get 243 times 2/3 to the first power, okay? And so you just have to figure out what that's equal to. 2/3 to the first power is still just equal to 2/3. And so what would be 243 times 2/3. Okay. If you put that in your calculator, you don't have to cancel first as long as you put the resulting fraction in lowest terms after that. Or you could cancel first, either way. 243 times 2. I had a little bit of an error there on the calculator. Let me try that again. There we go, 486. And then on the bottom, it's going to be 1 times 3 equal to 3. So we get 486 divided by 3. What is 486 divided by 3? Remember, when you try to put something in lowest terms, try to divide it first to see if it divides evenly. 486 divided by 3. If that doesn't work, then you can try the normal thing that you do when you put it in lowest terms. Try to divide the top and bottom by the same number and all that. But here, it does divide evenly. It's equal to 162 exactly. Since it's equal to a whole number, then that is, you can use that, okay? So yeah, try to see if it's a whole number first before you try to put in lowest terms. So we know what A1 is. We know what A1 is. We know what R is. That's all you need to know. Now, we can then plug it in. And since it says from 1 to 5 right here, you guys, that means we're figuring out S5, the sum of the first 5 terms. Let's look at that formula again. Okay, there it is right there. It says to put the A1 right there, which is 162. We just found that out. Put the A1 in front of the bracket. And then you say 1 minus, and then the R, which is 2/3, we put that in there along with the N, which is 5. Remember, N is 5 because it's the sum of the first 5 terms. All right. And then underneath that, it says 1 minus R. Okay. It'll be a little bit easier than the last problem, I promise you. Okay. It's still kind of tough because of that fraction, those fractions there, but we'll get through it here. What is 2/3 to the 5th? We got to figure that out first as we figure out what this fraction is ultimately equal to. Got to go inside the parentheses before we can multiply. 2/3 to the 5th is 2 to the 5th over 3 to the 5th. And that is equal to 32 over 243. Your calculator will confirm that for you. Okay. Let's write that down. While I'm at it, what's the bottom equal to? Remember, we got to figure out the top and bottom. You can do them both at the same time as long as you keep them separate. 1 minus 2/3 is the same thing as 3/3 minus 2/3. Because remember, 1 is the same thing as 1 over 1. Okay, if you multiply 1 over 1, if you multiply the top and bottom by 3 for 1 over 1, you're going to get 3 over 3. Remember, you need a common denominator since you're subtracting. What is 3 over 3 minus 2 over 3? 1/3. Okay, so we're kind of going along the same path that we went on in this problem up here, just the numbers aren't quite as big. Okay, what is 1 minus 32 over 243? Okay, same thing that we did here with this problem. Okay, when one of your denominators is equal to 1, then just like over here, that automatically means the other denominator is equal to your LCD. That means that the denominator, or the fraction that already has that denominator, is not going to change because, again, the goal is to make the denominator equal to the LCD. In the second fraction, it already is. But on this one, I need to multiply by 243, and then I'll be ready to subtract. What is 243 minus 32? That is 211, and then the 243 stays the same. On the bottom, the 243 stays the same. Okay, as it always does when you subtract. So we get what here? We get 162 times 211 over 243, like that. We're almost there, okay. What is 162 times that fraction? Well, if you want to multiply by a fraction, as we reminded you of in the last problem, you need to make the 162 into a fraction as well. Okay, you don't need to worry about doing any canceling here, okay. because of the fact the numbers are so big. But if you multiply 162 times 211, okay, that's going to be equal to what? 34,000. Your calculator can confirm this for you. 34,182. I'm just going to write it down since I already had it written down. Okay, but we know how to put that into our calculator. And now that you have, just like we did up here in the last problem, now that you have a fraction divided by a fraction, you can now do the reciprocal. Multiply by the reciprocal to figure out what the entire answer is equal to here. Oops. There we go. Again, when the numbers are that big, don't worry so much about canceling. Okay, just figure out what the fraction is equal to without doing that. But like I said, after you get down to this point right here, try to see if try to make it into a decimal or whole number on your calculator. All right, actually divide the top by the bottom and see what happens. It's better to have a more simplified answer like that if you can, because this is a pretty nasty looking answer with those big numbers, especially on the top there. So let's divide that. Okay, and if it's one of those nasty decimals that covers your whole screen, then we'll just keep it in the fraction form. But as you can see, it's not. It's actually equal to exactly 422. And so that's a much better answer to work with than to leave that big fraction there. So again, if you end up with a fraction answer, try to divide it top by bottom to see if it's either a fraction. I'm sorry, if it's either a whole number or if it's a decimal that doesn't cover your whole screen. Okay, that is better there, especially with these big numbers. It's just a better answer. Okay. And so that is number 5. Okay. Number 6 is similar, even though it doesn't look the same. All right. You don't need to turn it into a sigma letter problem like we did in 7.1 where we had a problem like this. What is different though about this problem, in fact, what is different about each of the next 3 problems is that, look at number 6. See how it says ... right here, but then there's nothing after that? That means that this is an infinite sequence. The fact that it says ... and then there's not like an ending there at all. There's no end to it. That means it's infinite. Okay, that means you're adding up numbers forever. Okay, kind of an interesting concept. We'll get into that more here as we go along, but we have a formula for that. All right, it's different than the one that we already did. It's actually easier. Okay, check this out. Again, this is on the front side of your worksheet. And you know what? I need to show you a little bit more here before I... Give me just a moment here. Don't want you to miss the details. There we go. Excellent. All right. See how it says here S, and then underneath the S? This is right above the 2 sigma letters that I talked about a few minutes ago on the front side of your worksheet if you're looking for it there. It says S and then an infinity symbol underneath the S. That infinity symbol indicates that it's for an infinite sequence. Okay, that's going to be the case on each of the next 3 problems. Because of the ... and there's nothing after that, this would be infinite. And then on the next 2, see how the top number, which is where the adding of the terms always ends? Okay, well that says infinity on both of these, so that means that both of those are infinite sequences as well. And so that's why we're going to use this particular formula in each one of these 3 problems. All right, let's start out with number 6. Notice here, in order to do this, you need to, again, know the same 2 things as before. You need to know the first term, which as you can see here is 4/3. And then you need to know the R. Do we know what the R is here? Let me write down the fact that A1 is 4/3 here first. Do we know what the R is? Remember, we can figure out what the R is, as we said earlier, by taking any term in the sequence and dividing it by the term that was before that. Just so long as you know the term that's right before that. Okay, so I could take 2/3, for example. I could take 2/3 and divide it by 4/3 because it's the term right before that. I apologize, that came up the screen. Let me say that one more time. You can take the 2/3 here and divide it by the 4/3 because the 4/3 is right before that. Remember, you can do that anytime you have a term in a sequence. If you divide it by, this is assuming it's geometric sequence, if you divide it by the term that's immediately before it, that will always figure out what r is equal to automatically. So, as you guys know, when we divide fractions, we can, and we should, flip the second one and then multiply. Since these numbers are pretty small, I'm going to do the normal canceling here. They're not big ones like before. And if I do that, you can see now here that the answer is 1/2. Remember, you're allowed to cross cancel only when you're multiplying. But since we are multiplying after we flip it, then cross canceling is okay. So we now know r. We now know 1/2. Let me move the r over here so you can see it in front of you here. 1/2. Okay, so then now that we know what the a1 and the r is equal to, we take our sequence, our sum formula that we have for infinite sequences here. Notice again that we only need the a1 and the r to plug into there. It's a much simpler formula. Let me go ahead and plug in those two things. The 4/3, as it says there in the formula. As it says there in the formula, it's going to go on the top because that's a1. And then the 1/2 is going to go right here because that's the r. Let me go ahead and do that. And then you just have to figure out what that fraction is equal to. Remember, as we've seen in previous problems, it's okay if you end up with just a single fraction on the top and bottom. Okay, and then you can do the reciprocal thing. But we do need to figure out what the top and bottom are equal to. All right. What is 1 minus 1/2? 1 minus 1/2 is the same thing as 2/2 minus 1/2. Okay, remember 1 is the same thing as 1/1. If you multiply the top and bottom of 1/1, you multiply the top and bottom by the 2, you get 2/2. And again, the goal there is to make the denominators the same because we need to subtract, okay, those fractions. 2/2 minus 1/2. 2 minus 1 is 1. The denominator stays the same, so you get 1/2. 1 minus 1/2 ultimately is 1/2. Now that I've got a single fraction on the top and bottom, I now can do the reciprocal thing. Nothing cancels there. Since they're small numbers, though, I'm going to try to cancel here, like I was saying before. When the smaller numbers are there, it's okay to try to do that. But nothing cancels. So then when I multiply together, my final answer is 8/3. Okay, so that entire thing right there adds up to 8/3. And so you might be wondering to yourself, how in the world can something that goes on forever, a bunch of numbers that are just being added together infinitely, you just keep on adding forever and ever and ever, which is what an infinite sequence is, when you're taking the sum of it, you're adding forever and ever and ever. You're not just adding the first 5 terms like in the last problem, or the first 10 terms like in problem number 4 right above that. You're adding infinitely, okay? The terms go on forever and you're adding them all up forever and ever. How in the world can it eventually converge on this one answer if you just keep on adding? Shouldn't it just keep on going? Well, what happens is that r, because of the fact that r is equal to 1/2, what's going to happen is that if you keep on multiplying by 1/2, it's going to make the number smaller each time. 4/3, 2/3, 1/3. Each number is going to be smaller than the one before it. And so what ends up happening is that since it keeps on getting smaller, eventually as you go out towards many more numbers that you're adding up here as it goes along past the 1/3 and more after that, you're eventually going to be adding numbers that are so small because they keep on getting smaller that eventually the numbers are going to be really close to 0. All right, and if you're adding numbers that are really close to 0, what happens? The answer doesn't change, does it? Like, for example, if I add together 8 plus 0, it's still going to be 8, right? 11 plus 0. It's still going to be 11, right? So if you're adding numbers that are really close to 0, likewise, it's not going to change much. All right, and since it keeps on getting smaller and smaller, eventually it's going to hardly change at all. And so that's why it's not a surprise that the answer eventually converges to something, because as those numbers get really small, you're going to get really, really close to 8/3, and then eventually you're not adding hardly anything at all. And so the 8/3 is where you end up when you eventually get to the numbers that don't contribute anything at all. You're not adding anything at all. So when does this happen, though? It all depends on what the R is, okay? If the R, there we go. If the R is between -1 and 1, as you see here on the front of the worksheet when they talk about infinite sequences again, if the R is between -1 and 1, then this will happen when the answer will eventually converge on a number such as 8/3. Okay. However, if the number is not between 1 and 1, which we will see on the very last problem, number 8, then there will not be an answer because it won't converge on a number. I'll talk about that more when we get to number 8. Okay. So when you have a sum where you're adding up an infinite number of terms, okay, and again, this is when you're talking about geometric sequences here. When you have adding up an infinite number of terms instead of just 5 terms like in the last problem or 10 terms in the one before that, you have to realize that you're only going to get an answer in that case if the R is between -1 and 1. Okay, so let's keep that in mind, very important. But if you do have a R between -1 and 1, then this is the formula you use if you're adding up an infinite number of terms instead of 5 or 10 terms. Okay? Okay, moving on to number 7. You'll see that it's a sigma letter, but you'll also see that there's an infinity symbol on the top. That means you plug in every number from 1 to infinity, which implies, just like in the last problem, that we're going to be adding up an infinite number of terms. So it's going to be it's going to be a sum of an infinite sequence. Okay. Not just adding up the first 5 terms or the first 10 terms like we've been talking about in problems 4 and 5. So because of the fact that it's in this form right here, pardon me, it's actually in this one, but either one of these is the same as far as what it's going to end up being. It's going to be a geometric sequence in either one of these cases where you've got a constant, 5, for example, in this current problem. Then you got another constant inside the bracket, -1/4 in this problem. And then you've got I minus 1. As long as it starts with 1 and goes up to what, this could be anything here, then it will be a geometric sequence, and the number inside of the bracket will be your R. Now, I said that the number on top of the sigma letter could be anything, but because it's infinity, that means that it's going to be the sum of an infinite sequence. Okay? So what we're going to want to do then is do S infinity, the S infinity formula, not the Sn formula from problems 4 and 5. Okay, and it's all because of that symbol. So we just now need to know what A1 is, the first term of the sequence, and that can be found out by plugging in the number down here at the bottom. That number, when you plug it in, will always give you the first term, no matter what it is. And so if I plug that in, I get 5 times -1/4 to the 1 minus 1 power. Okay, and remember, you got to figure out what the exponent's equal to before you can take -1/4 to that power. That's the order of operations. But because that exponent is 0, 1 minus 1 is 0, anything to the 0 power is equal to 1. Remember, we've said that a number of times before. Anything to the 0 power is 1. So we ultimately end up with 5 times 1, which is 5. And so putting all this together and realizing that, like we said a few minutes ago, since R is between -1 and 1, okay, since R is between -1 and 1, -1/4, If you put that in your calculator, for example, it would be negative 0.25. That's between negative 1 and 1, okay? Just like 1/2 is equal to 0.5 if you put in your calculator, if you didn't know that already. And we know that that's anytime you have 0 point something or negative 0 point something, that's between these two numbers, negative 1 and 1. So because it's between negative 1 and 1, that means that we're going to get an answer that it's okay to use this formula. It is not okay to use this formula, as we'll find out in the next problem, if r is not between those two numbers right there. Okay, but we can in this case. So let's see how it comes out. So since the top is where we're supposed to put the A1 number, I put the 5 on top. And then underneath that, we say 1 minus, and then remember, r is negative. And when you plug in a negative number behind a subtraction symbol, okay, if there's a variable that's being subtracted and then you plug a negative number into that variable, we've seen this on a number of occasions this semester, that's a double negative. And so 1 minus negative 1/4 is going to become what? It's going to become 1 plus 1/4. Okay, so it's minus up here because you plugged in a positive number behind it. It stayed as minus, but because you plugged in a negative number behind the minus sign this time, okay, it's a double negative, and that's why this becomes plus. Now we need to figure out what this fraction is equal to. That means you got to figure out what the top and the bottom are equal to there. 1 plus 1/4 is the same thing as 4/4 plus 1/4. Remember, you need a common denominator since you're adding a fraction to something. You make the 1 into a fraction in that case so that you can add the two fractions together. Common denominator is 4. We add and we get 5/4. Now, anytime you're dividing, same thing with adding and subtracting. Anytime you're dividing or multiplying, if one of the two numbers is a fraction, you want to make the other one into a fraction also. Okay, so that you can then execute that operation on the fractions. In this case, the operation is division. Okay, so if one of the two things you're dividing is a fraction, make the other one into a fraction also. Just like we did with the addition over here. Okay, one of them is a fraction, you got to make the other one into a fraction also. Anyway, that means we take the reciprocal of the second fraction, like we always do when we divide. We can cross cancel here. Not a bad idea since these are small numbers. And we end up with 4/1, which is 4. So our final answer there is 4. And that means that this entire thing right here, even though you're adding up an infinite amount of numbers, because of the fact that r is between negative 1 and 1, the answers will the numbers that you're adding up will eventually get so small that they will eventually converge, and the number that they will converge to is 4. Just like on the previous problem, they converged to 8/3. Okay, but will it always converge? Now, as I already said, not always. If you have a geometric sequence and you're adding up an infinite amount of terms and the r is not between negative 1 and 1, that's a different story. Let's see an example of that right now. Okay, and finally here in number 8, once again you can see that it is in the format of BRI, okay, where you've got the constant and then another constant inside the bracket and then the variable and the exponent. So that means that the r is what? The r is 3/2, but stop right there, okay? Remember I mentioned to you just a few minutes ago that when you're doing infinite sequences, which this is, okay, this is going to be infinite sequence, or infinite sum, I should say. Okay, you're taking the sum of an infinite sequence. Let me write that. Sum of infinite sequence. You're not just taking the sum of the first 10 terms or the sum of the first 5 terms or something like that. It's sum of all of the terms infinitely. When it's a sum of an infinite sequence and the r is not between negative 1 and 1, then what does that mean? Remember, we mentioned a few minutes ago that if you're doing an infinite sequence and r is not between negative 1 and 1, then there will be no answer. Okay? So when it's infinite and r is not between -1 and 1, for those two reasons right there, you guys, the sum diverges. Diverge is the opposite of converge, right? Okay, I sound like an English teacher, I know. But diverges means that it's never going to converge on an answer. In the previous two problems, in number 6, it converged on 8/3 because the numbers that you're adding up get so small that eventually it converges in on one number, 8/3. Same thing here. The answer converges in on 4 because you're eventually adding up numbers that are so small because the r is between -1 and 1 that it eventually will converge towards 4. Okay, so as you get really close to 4, in other words, all right, the numbers are so small that the answer is not going to change as you keep on adding up more numbers. And so it converges on 4. Okay, this one will never do that. Because when you multiply every term by 3/2 in order to get to the next term, you guys, what's going to happen? The numbers that you're adding up are getting bigger than the numbers that you added before that. And so it's just going to get bigger and bigger and bigger. And it's never going to get small. It's never going to really small close to 0 like the other ones did. Okay. And so there's no way it could ever converge on an answer. So 2 reasons. Infinite sequence. R is not between -1 and 1. There is going to be no answer when you try to take the sum because the sum diverges. All right, you'll see that word come up in your homework. It again means these 2 things right here. Okay, so watch out for that. All right, so that concludes part 2 here and also concludes the section 7.3 overall. All right, and so again, let me know if you have any questions or if you have any concerns about that. And you have a good day. You take care, and we'll see you back for a section 7.4 in the next video.